Hi, I'm Jonathan Walsh, a mechatronic engineering student completing a professional experience project. The Modular Economical Sonar Buoy Heuristic, or MESH, is a low-cost passive sonar surveillance system designed to detect and classify marine vessel acoustic signatures. The project was proposed to investigate the trade-offs between hydrophone instrumentation quality, embedded processing capability, classification accuracy, and power consumption within a deployable sonobuoy prototype platform. The focus is not on defense-grade surveillance, but on demonstrating the feasibility of an economical and reusable acoustic monitoring platform. Following the literature review, the minimum viable product was defined as the comparative evaluation of representative statistical, deep learning, and hybrid classification methods. Initially, this was intended to use underwater acoustic propagation simulation tools, such as ActUp and MATLAB. However, further investigations revealed that these tools primarily generate simulated acoustic environments through the modeling of input signals, propagation paths, impulse responses, and environmental noise. Since the project objective is classification performance rather than acoustic propagation modeling, this simulation-heavy approach was determined to be unnecessary. As a result, the focus shifted towards benchmarking classification algorithms directly, using public underwater acoustic datasets on the desktop, and then evaluating them against computational resource consumption and inference performance on the Raspberry Pi 4. The software component of MESH began as a collection of independent scripts for feature extraction, dataset building, and model training. Whilst functional, the codebase relied heavily on hard-coded file names, parameters, and output locations, making experimentation difficult and reducing reproducibility. The first major milestone was reconstructing the project into a framework rather than a collection of scripts. Configuration files now define what things are called, path management defines where things live, and settings define how training and inference is run. This separation significantly improves maintainability and reduced duplication across the codebase. The project currently supports multiple classification approaches, including statistical methods, deep learning methods, and hybrid methods. Performance metrics are collected and stored automatically for comparison against computational complexity and resource usage. The next major milestone was building a graphical user interface using custom tkinter. The GUI transformed the workflow from a command line driven scripts into an integrated research platform. Current pages include dashboard, dataset management, training, results, and settings. The training page dynamically loads available models from the central registry and provides a reusable console for monitoring experiments. Result pages automatically display benchmark outputs and confusion matrices for analysis. The project has evolved from isolated machine learning scripts into a configurable and reproducible acoustic classification framework. The next major milestone is deployment. A deployment page will be created to inspect available trained models and export the required files into a deployable Raspberry Pi package. A single export button will package model files, metadata, and labels for transfer to Sonobuoy. Additional Raspberry Pi software development includes battery monitoring, GPS integration, IMU integration, data logging, and remote configuration. After deployment is operational, LoRa communication will be integrated. As for the hardware design process, it also follows a systems engineering approach. Rather than designing the buoy first, the process began with unpackaging the internal components and designing outward. The sequence was components layout, enclosure design, buoy design. Component envelopes and masses were estimated for the Raspberry Pi, battery, hydrophone electronics, GPS, LoRa module, and IMU. Early work focused on buoyancy force and stability calculations to determine the volume of the buoy and the positioning of the payload masses. This enabled the development of a removable electronics capsule architecture. Importantly, the hydrophone analog to digital conversion is independent of the Raspberry Pi GPIO pins, simplifying troubleshooting and reducing integration complexity. The waterproof seal itself is provided primarily by the O-ring and cable penetrator arrangement. The buoy and enclosure are intended to be printed in PETG because of its strong layer adhesion, impact resistance, and suitability for marine environments. The Makerspace Bamboo Lab A2L supports fabrication of the current buoy design. Scaled down models shall be printed on Monday, the 27th, to verify the screw lid's functionality and buoyancy calculations. The final phase of the MESH focuses on deployment, operational testing, and project closeout. Thanks for watching. Feel free to check out the plans for the rest of the project on my website.